Hello folks, welcome to CS-412 Software Security. This is the speedrun of OXOC and we're going to talk about a case study, namely the web. The learning goals for today are as follows. First, we want to understand the security properties of server systems and how they differ from regular desktop systems or mobile systems or whatnot. Then know the limitations of mitigations for such systems, as in how to customize the protection on the server side for these particular systems and areas. And then we're going to talk about OWASP top 10 as a large chunk of today's class. And here we would like to know the details of the different attack vectors or threat classes, and then kind of differentiate between potential mitigations and whatnot, and how to bypass and protect against these kind of attacks. So let's start with the kind of overview for today's class. The web and the internet has two different views of security. Well, one of them is that anything running on a server is just a long-running program with a network input and output, right? So anything that you run on a server is just like a regular application, just that it runs a little bit longer. And this may change the attack scenarios a little bit. It's also a complex application with multiple layers and components and whatnot. And the other perspective is this kind of differentiated web-specific attack vector. So we're going to here apply software security principles to guard Daemons and then rethink exposure and threats for web services according to the OWASP definitions. They did a great job at actually defining potential issues there. But we're going to start with the software security kind of view first, especially from a systems perspective. Let's talk about daemons, or also called services and servers. A daemon is just a long-running service that serves outside requests. So for example, a web server, a mail server, or a DNS server are all examples of daemons. And they connect, they allow connections from the internet, and then they serve specific requests. One of the issues is that they are actually prone to attack, and they are the prime attack vector to compromise a server system, right? So they are long running, they are complex, and they are exposed. The complexity is due to the need to serve a lot of requests at the same time, concurrently, for different users. So they're usually multi-process, multi-threaded, multiple processes. There's different levels of caching for optimization purposes, and they often have a broad or diverse set of configurations and functionalities. So if you think about the Apache web server, it comes with like hundreds of different modules that can be loaded, configured, adopted, and whatnot. Also, daemons are exposed. They are directly connected to the internet, and they actually expose a connection to the internet. So anybody, or pretty much anybody, can connect to the service and then interact with it and trigger interesting functionality. This is different from a client's perspective. For a client, the client connects to a particular server, right? So an attacker would first have to compromise the connection to the server and impersonate the server to gain access to the client. Whereas for the server, anybody on the internet, potentially without accounts, can connect to the server. So let's look at these individual features in a bit more detail. Daemons are long running, right? So this means that the different probabilistic defenses and mitigations, such as ASLR and stack canaries, could be mitigated or could be bypassed by leaking the actual secret. There's one secret per process or one secret per thread. So if multiple attacks can be triggered, right, then the leaked information can be used by the attacker in a later request. The heap layout is influenced by concurrent allocations. So attackers, by triggering multiple requests, can massage the heap into a particular layout to then trigger certain layouts, whatnot, that would allow the attacker to place specific objects next to each other that can then be useful in the later attack. And yeah, the most general issue is that information leaks become extremely dangerous and would allow the attacker to use that information across subsequent attacks, maybe like minutes or hours later, right? So this takes a very long time. Daemons are also complex, right? Often there's this trade-off between reliability and security attacks, and usually or often a standard practice is that servers that crash are simply restarted, right, to ensure availability. So there's a trade-off between availability and keeping servers down after a crash for debugging purposes or whatnot. And if a server is restarted, this gives the attacker readily another shot at actually compromising the service because it just restarted, it's available again. Also, the large set of functionality increases the attack surface, and shared secrets across users in a single address space also make this easier for an attacker to compromise. Daemons are also exposed, right? So they service a lot of concurrent users in the same address space. So if you think about it, a mail server will be potentially one single process that accepts hundreds of connections via individual threads. So in the same address space, you are currently serving multiple users at the same time, right? So potentially the administrator could be logged in on a connection on the same server that you are logged in as a mer user, or even worse, as somebody who's just trying to send an email to the target address. As I already mentioned before, outside connections are allowed, and attackers can also leverage many diverse and different IPs. This makes it hard to, for example, limit the amount of connections on a per IP basis. Now, we could discuss if we can rate limit accounts or how much we can rate limit accounts, but this also adds additional complexity and makes it again harder to reason, and potentially would allow an attacker to trigger a denial of service for a given account by trying to compromise that one after some time, right? So there's interesting trade-offs to slowing down attackers versus prohibiting legit users from actually working with the service. Now, to protect daemons and services, compartmentalization is a key approach, and we've seen this very early on for SendMail versus QMail, where QMail is broken into a bunch of different components. So break complexity into smaller components, develop fault compartments which can fail independently and be restarted if needed, but don't have any additional privileges as the minimum needed. The goal here is one component can fail, but others continue to function, allowing interaction. So servers are not just long-running user-space application, but they require additional customization, especially because they are massively exposed to potential attacks, and we therefore require customization, specialization, and like a special note on the security for the accounts. Let's now look at the OWASP side of things, the second kind of viewpoint. And here we'll discuss the OWASP Top 10. OWASP stands for Open Web Application Security Project, and it originally started for just evaluating the security of web applications, but it's also true for any kind of internet connected service in general. So it's been generalized quite a bit. So the Open Web Application Security Project collects information about vulnerabilities and attack vectors. And every couple of years, they release the top 10 of vulnerabilities, as in the biggest threats that can happen to individual applications. The latest or most recent version was released in 2021. The previous versions were from 2013 and 2017. So every 4 or 5 years, a new version is being released. The current top 10 that we're going to now talk about in a bit more detail is as follows. Broken access control, cryptographic failures, code injection, insecure design, security misconfiguration, vulnerable and outdated components, identification and authentication failures, software and data integrity failures, security logging and monitoring failures, and server-side request forgery is number 10. So let's go through them in a bit more detail and discuss what the potential issues are. Let's start with broken access control. This is the top one threat for web application or internet applications. And access control has a very long history of being weak or not implemented correctly. So access control limits or restricts authenticated users or users in what they can do. And broken access control means that users are not correctly limited, so they can do more than they should be able to do. An attacker can exploit these flaws to access any kind of unauthorized functionality and or data, such as, for example, switching from one user account to another user account, view files of other users that they shouldn't be viewing, modify data of other users that they shouldn't be able to modify, change access rights, and so on. So potential examples of such missing access control or broken access control are unprotected access to the administration interface. This was a common issue with web applications where if you just knew the secret URL, you would be able to log in as administrator and reconfigure the system accordingly. Access to backend services such as storage, like for example to upload individual file onto the web server that could then be potentially interpreted as code. Access to the database interface without restriction. So if the user, the unprivileged user, can execute arbitrary SQL statements, this is an unintended feature. Access to backend services, for example, through a REST API that should not be exposed to the public is another example. And there's a bunch of different such use cases. To protect access control, well, the deny by default policy is a good starting point. So everything except the public resources should be flagged as denied by default. The exposure needs to be limited. For example, if something crashes, instead of giving a stack dump of the web application, a simple error code would suffice. You should disable directory listings, rely on central access control to keep track of the settings, and ideally rate limit API calls and enforce access checks in each individual API. And then in addition to that, you need to log access control failures and actually check the logs periodically to see if somebody is trying to escalate their access or is actually successfully able to do so. The second OWASP top 10 feature is cryptographic failures. So many web applications and APIs do not properly protect sensitive data, such as this could be financial, healthcare, and personal identifiable information. So attackers may want to steal or modify such protected data and could be compromised without extra protection. So we're looking for confidentiality and integrity for these cases, and this is where cryptography actually comes in. So the data should be encrypted while it is in transit or at rest, and this requires special precautions, of course. Why is it so hard to protect? Now, this is an interesting challenge, right? One of the big issues is that personal information or personal data is incredibly hard to change, right? Only because your birth date leaked from a page, you're not going to be able to change it, right? You cannot change your birth date. Same as you cannot change your fingerprints. Renewing a credit card is super annoying, but changing a name or birthplace or whatnot is incredibly is next to impossible, and most people would be unwilling to do that. So this means that exposure of this personal identifiable information cannot be undone. So these records with names, emails, birth dates, or whatnot, or so on, become incredibly worthy for attackers, because somebody's information that leaked will likely not be changed, and it can be resold several times. As soon as the information is public, it is gone. Protecting one's identity becomes much more challenging. As it turns out, sensitive data is very frequently exposed. So there's breaches happening every now and then. It's partially a result of a business strategy, as companies are trying to store as much data as possible of any given users. The assumption of companies usually is data is the new gold, right? We want to keep as much information of our users as possible, and we're going to ask as much information as possible. As soon as a company decides to store data for later processing, any information leakage can actually result in a full loss of that data that's been stored. So when you're designing services, one of the key goals is to only store the bare minimum of data. If you cannot leak any data that you haven't stored. So store and process the minimum amount of sensitive data, separate and segregate data into compartments depending on their use cases, and then create data policies that record where, how, and what data is processed. And again, data that is not recorded cannot be stolen or leaked. So protecting sensitive data is essential for these web applications. Be aware of what kind of data you're handling, why you're handling it, and have a good justification of why the data is actually necessary. Only store what you need, nothing more. Protect data both at rest and in transit. And for example, for passwords, this is a no-brainer, but only store salted hashes and make sure that they cannot be leaked in any way or form. The next top item is code injection. That's going to be the item that we're going to spend most of the time on. And code injection is a very common attack vector. And this used to be the most common attack vector in application security, as we discussed earlier in this class. And it is one of the top attack vectors for web applications, as we'll see. We're not going to inject machine code into a web application, but code injection can be SQL, NoSQL, commands, LDAP injection, or whatever. And these kind of injection flaws occur when untrusted data is sent to interpreter or as a part of a command or a query. The attacker's data can trick the interpreter into executing unintended commands or then accessing the data without the proper authorization. Code is not just executable instructions. Web applications execute some higher level of code, which could be under control of an attacker. So log4j is an example, and there's a bunch of other examples that we'll now go through. Command injection is a common vector, and it follows the kind of philosophy of Unix systems to leverage simple tools to achieve complex results. And oftentimes web applications will simply call a shell command to trigger some processing. So data is passed to scripts or programs as parameters. And now as you're passing information from the attacker to an actual program, you may not be vetting, or applications may not be completely vetting the parameters. So the constrained communication channel will contain both code and data. For example, the query command and the query arguments. And then the potential issue here could be that you could escape to a shell and then trigger any kind of additional processing because you're not escaping arguments correctly, right? So dynamic web pages execute code on the server, and this allows the server to add content from other sources, for example, databases, to provide rich interfaces to the user. These web pages, dynamic web pages, often combine complex parts dynamically and then send the final result to the user. And as part of this combination, they could rely on some kind of local system or some shell commands. So if you look at this very, very simple PHP program here, we want to, this implements the functionality to display a file. So you can give it a parameter, which should ever be the file, and it just calls system cat the name of the file parameter, and then returns the output from that. Now, if you look at this, well, the functionality will actually work. You can use this to display a file, to include the contents of a file on the local file system, but there's a couple of security issues here, right? So there's no separation of code and data. So the benign execution would be simply to pass a file name that is then being displayed. But an attacker could do, for example, display.php p file equals x.txt, and then add a semicolon to chain and add another command. So we're catting etc password in addition to that, right? So /etc/password. So this would contain both the contents of x.txt plus whatever is written in etc password. So a system is a powerful command that executes actual full shell scripts. So how can we kind of mitigate this attack vector? So what are reasonable mitigations for that? We could just block the semicolon. That's a start. But deny listing is not a good solution, as the attack space may be infinite, right? We could be using a pipe. We could be using a backtick. The attacker could be using other commands, so cat instead of or remove instead of cat. Even the shell has many built-in commands that could be used to trigger additional functionality. So what are reasonable mitigations for code injection? Well, you could validate. That's the first one. Ensure that the file name matches a set of allowed file names. So do allow listing instead of deny listing. Remove any non-alphanumeric characters. Hardcode directory and set of allowed files to like look up against a list. And disallow any kind of special characters in the file name would be one example, right? So be careful when you're looking up, when you're working with the shell scripts, and make sure that the data that is being passed to them is highly limited and constrained. You could look at escaping. Well, you'll have to escape parameters so that the underlying interpreter, here the shell in this case, can distinguish between the data channel and the control channel. For example, cat quote file.txt end quote, right? So we would be constraining the file name to the minimum amount here, and make sure that you cannot contain additional code. So we would separate the data channel and the code channel. Now, how do you write such an escape function? And one of the biggest lessons here is that you shouldn't write your custom escape function. There's always going to be one feature that you miss. There's libraries out there that provide these kind of escape functions. Each language environment has its own flavors of escape functions that you can use for the context. So when you're writing an application and you need to call a shell script, you need to make sure that you're actually calling the correct escape function is available in your runtime system. Third option, well, you could reduce the privileges. System is extremely powerful as it launches a new shell interpreter. And you often don't need a new shell interpreter, right? So limit to the simplest possible API. Open the file yourself, read it into a buffer, or if you must execute a command, launch it directly, not through the shell. So in this concrete example here, we could just use the PHP internal function file get contents of the file name, and this would be perfectly sufficient to introduce this information. So what enables these kind of injection attacks in general? Well, both the code and the data share the same channel, right? They're sent through the same channel, and the data and the code are being intermixed. In the system example above, cat and file are specified as part of the same shell script, where like the semicolon could be used to start a new command. In code injection, the data on the stack and the executed code share the same channel as the code pointers, right? So this is the similarity between application security and web security here. If we go to another example, let's pick SQL injection here. We've got this SQL statement, select all entries from users where emails equals email and password equals password, right? This looks like a perfectly reasonable SQL statement. It gets the job done, but it would allow an attacker to inject like a tick to escape queries and to inject commands. Well, also as a side note, the password is stored in plain text and not hashed, but this is for another security issue. So SQL injection is, in spirit, the same attack as code injection or command injection that we just discussed, right? So it allows the attacker to inject some new information into the target area. So for SQL injection, we require additional checking, validation, escaping, or reduction of privileges, similar to command injection. We want to separate control and data channel, for example, by running prepared SQL statements. And the prepared SQL statements, similar to printf, we're defining the format and then just adding the parameters at the back and making sure that they can actually be included. So how do you prevent code injection? Well, use a safe API, such as prepared SQL statements or restricted commands for command injection. You validate the input based on an allow list, and you reject any kind of invalid inputs. For any remaining dynamic query data, you escape commands using available API, and you should never roll your own escape functions on that. The next one is cross-site scripting, right? Cross-site scripting allows an attacker to inject and execute malicious JavaScript or other kind of content in the context of another web page. So for example, malicious JavaScript code that is injected into the banking web page of a user. So here we're injecting code into another web page. And this is another common attack vector. There's three kinds of cross-site scripting: persistent, stored XSS, reflected XSS, and client-side DOM XSS. And this depends on where and how the data is actually being injected. So the attacker, in persistent cross-site scripting, the attacker stores the data on the server itself. Right, so imagine, for an example of persistent cross-site scripting, imagine a chat application that stores chat messages of all the participant and then just provides it to all the others, right? So the attacker could send a message that contains script alert Mr. Evil here and script. This is being stored on the server, and as individual clients pull the latest messages, the message is being sent to all of the clients where it is executed on their end, triggering the JavaScript command on their systems. So this could be feedback forms, blog comments, or even product metadata. So you don't have to see it to actually execute it. Here the bug is on the server side where the filtering is not being done. Reflected cross-site scripting. Here the attacker does not store the JavaScript data on the server, but actually encodes the attack data in the link that is then sent through an email or a compromised site or whatnot. So this the domain looks legit, but as part of the link, the attacker injects some kind of JavaScript that is then reflected back to the client. So web interface may return your query as part of result. So for example, your search for query return 23 results. So one of the requirements here is that the user must actually click on the attacker controls link, because the link encodes the JavaScript side. But the bug is still on the server side where the input is not filtered correctly. There's client-side cross-site scripting, which is the last kind of cross-site scripting. And here the issue is that large applications contain lots and lots of JavaScript code. The code itself may contain vulnerabilities. The JavaScript may use these URL parameters to process information. Think of AJAX or JSON requests to process data in the background, similar to how Gmail loads new emails and whatnot, or sends emails. The attacker makes the user follow a compromised link, but compared to the reflected cross-site scripting, the server does not embed the JavaScript code into the page through the server-side processing, but the user-side JavaScript parses the parameters and misses the attack. Think of sending a user an email in Gmail, but the email is being parsed on the user side, and through that it triggers a JavaScript cross-site scripting error. Right here, the bug is on the client side and in the server provided JavaScript that is being pushed to the client. Now, mitigating cross-site scripting is a big topic, and modern web frameworks actually allow you to properly escape your input. Each framework has its weird subtleties, so be careful and use provided escape functionality whenever you look at working with such a web application. You could also leverage data flow to detect where any kind of unfiltered input exists and then flag this from a framework perspective. Now, to summarize code injection, the third of the top three, you need to separate data from the web application logic. So isolate the data flow and the control flow and keep the two channels separate. Limit data exposure and access. So one database user for access, another one for administration, another one for writing. Use safe API functions and validate based on an allow list. And then next one, top 4, is insecure design. This is kind of a fuzzy, weird item due to the lack of threat modeling and explicit list of threats, lack of focus on secure design patterns and principles, or fuzzy catch-all area that covers any kind of abstract issues that are somewhat unexpected. Top 5 as another a bit more interesting one, security misconfiguration. This is a result of insecure default configuration, incomplete or ad hoc configurations, instantiations, unprotected cloud storage, allowing an attacker access to it, misconfigured headers, error messages containing sensitive information or whatnot. So not only do you need to securely configure all the operating system, frameworks, libraries, and whatnot, but you also need to patch and upgrade it in a timely fashion. Some misconfiguration examples. A service uses the example demonstration configuration that allows way too much functionality that is not limited. The development configuration is deployed in production without actually reducing access to it, with detailed error traces, debug output, and any kind of auto log output that should not be seen. Or any kind of libraries that you're using is not vetted and not protected. Many older or poorly configured XML processors evaluate external entity references within XML documents. External entities can be used to disclose all kinds of internal files using the file URI handler, internal file shares, port scanning or whatnot, and just provide a large amount of functionality to attackers. So make sure you don't include external or untrusted resources, otherwise go back to top number 1. You need to sanitize user uploaded data, and ideally instead of XML you may want to use a simpler format such as JSON. Don't serialize sensitive data, and disable XML, external entities, and DTT processing. So there's the billion lols attack, and if you actually try to concatenate all the different entities together, you see what the potential issues are. And I encourage you to actually count the number of lols that are added to this example. So how do you prevent misconfiguration? Well, you have to document the configurations you use, what software it is, what version, in what configuration, what the settings, and why you chose different settings. You need to keep the systems up to date. You need to compartmentalize individual services and periodically review for configuration changes or failures to keep up to date with whatever the development gives you. Point number 6, vulnerable and outdated components. And this is something that is becoming more and more important. Bugs will multiply. There's going to be more bugs in software than you can count, and you want to keep track of all the libraries, components, frameworks, operating system patches, software modules, and so on that you're using in your application. They continuously update those targets. You want to know which functionality is being exposed by your web services, and then keep track of the potential CVEs or vulnerabilities that have been filed against that to continuously update it. You can remove unused dependencies to lessen your attack surface. Document your components and dependencies. Also see top 4 and 5. monitor any kind of unmaintained libraries or components to remove and update them as quickly as possible. And in short, you just need to do better DevSecOps and keep track of all the different codes that you are using in your system. Top 7, identification and authentication failures. Well, application functions related to authentication and session management are often implemented incorrectly, unfortunately. So as a basic mitigation strategy, simply use the built-in functionality. Don't roll your own. If there's any issues, this could allow attackers to compromise password, keys, session tokens, or whatnot, or to exploit other kind of implementation flaws. And attackers are often shifting nowadays to away from passwords a bit towards session tokens, especially because multi-factor authentication seems to become more common, right? Multi-factor authentication, as a quick reminder, requires a second factor at least. So you're logging in with username and password, and then you're confirming the login by replying or typing an SMS, text message, email, or whatnot. Now, as multi-factor is being rolled out, attackers are often trying to steal the session key that is being embedded after successful multi-factor authentication, which allows them to kind of take over the session at a later point. Another point, never use default credentials on any of your systems. Develop a reasonable password strategy based on lengths, strengths, and checks. Don't make it too insane, otherwise users will just try to bypass the password. Limit or delay failed login attempts and log any login failures. So the most common attack vector in this category is forgotten admin pages. So many web services have a default administration page, such as administrator, WordPress admin, admin and many others, or login or whatnot, right? So if you ever run a web service, you will see that there's a ton of tries from automated bots that try to find these pages as quickly as possible. You cannot assume that an attacker will not guess these URLs, because there's sufficient amount of lists out there that provide simple examples that attackers can use. An attacker may guess these hidden URLs, and you need to protect these interfaces with a strong password, and a default credential is not going to be sufficient. So, how do you prevent authentication vulnerabilities? You implement second factor, never deploy with default credentials, test registration, credential recovery, and API usage against attacks, rate limit failed login attempts, and use a server-side secure session manager to only send the random session ID to the user and not embed any additional information into any of the cookies. Number 8, software and data integrity failures. This is one of my favorite ones. Insecure deserialization often leads to remote code execution. I just want to remind you of Log4Shell, which was a big issue recently. Even if deserialization flaws do not result in remote code execution directly, they can be used to perform attacks. Replay attacks, injection attacks, and privilege escalation attacks. The biggest issue is that it may be convenient to just store information in a cookie, such as ID, name, role, password hash, and whatnot. An attacker can actually gain admin access by just encoding the corresponding field, making herself an admin. Other examples include pickling or unpickling of objects, or providing an array instead of a string, which results in issues for many different dynamic languages. Mitigating insecure deserialization. You can add integrity checks. You can enforce type checks during deserialization and make sure that you are actually receiving what you expect to receive. You can isolate parsing code to deprivilege process, and you can log deserialization exceptions, for example. Number 9, insufficient logging and monitoring. If you couple insufficient logging and monitoring with missing or ineffective integration with incident response, this allows the attacker to further attack systems, maintain persistence, pivot to more systems, and tamper, extract, or destroy data. Right, so here the issue is that most breaches are detected very late. A company may only learn that it has been attacked a couple of 100 days after the actual attacks, and is often informed by external parties. And this is still true except for ransomware, where the attacker will actually notify you fairly quickly that you have been attacked. But then they are also going to demand a ransom. So one of the issues with insufficient logging is that companies are often overwhelmed with the amount of log messages that they get. They've got several log analysis frameworks running in parallel. A lot of threads are being highlighted, and these threads may not be analyzed quickly enough, so adversaries could extract the data. Brute forcing logins is noisy and results in millions of log entries. It's kind of hard to figure out if the brute force has been successful or not, which could kind of drawn out the actual successful attack in a lot of noise. Ensure errors are logged and that the log files are evaluated and actually processed automatically. Then follow an audit trail for important transactions and clear responsibilities. Number 10, server-side request forgery. Here the attack vector is that you can trick a server to open a request towards the internal network. Imagine that the web application is running in a demilitarized, or the server is sitting in a demilitarized zone where it has access both to the internal network but also to the external network. So the server is actually dual hosted. The attacker tricks the app to query the internal network by sending a request to one of the internal services and then expose that data to the attacker. So this allows the attacker to turn a web service into a VPN client, allowing it to access internal network data. So this is according to the study. This is in the process of becoming a threat. It doesn't show up in active monitoring yet, but it was added based on community feedback as perceived to be the most interesting upcoming attack vector. So these were the top 10 that we looked at that are currently defined. Let's look at the evolution of attacks over the last 10 plus years. Code injection used to be the top 1 and 3, with A1 and A3 being both forms of code injection that remained around for a while. In 2013, there were a couple of additional issues such as insecure direct reference, missing function level access, and so on that were out there and have been actually merged into broken access control and thereby reduced their impact. From 2017 to 2021, we saw that code injection has been reduced quite a bit, but access control became much more important. And insecure design, software and data integrity failures, and server-side request forgery became new interesting angles that were not around before. So to summarize, OWASP top 10 consists of code injection, broken authentication, sensitive data exposure, XML external entities, broken access control, security misconfiguration, cross-site scripting, insecure deserialization, using components with known vulnerabilities, whatnot, logging and monitoring. So these are a lot of different threats, and we can kind of summarize 3 big themes: input parsing, authorization, and configuration and documentation. For input parsing, code injection is a big theme that is extremely important, same as we've seen from software security before. Different to software security, authorization is another like big pillar in web application security, because you have actual untrusted users connecting to these services. And then supply chain configuration and documentation also becomes more important as we move forward. To summarize, Daemons are long-running, complex, and exposed, and we need to provide special customization for software security practices for these targets. Compartmentalization helps reduce the attack surface, and we need to customize mitigations towards this particular use case. Code injection is a powerful attack vector both for the actual server implementation, but also for the high-level web application services. And here, separation of code and data is crucial. We also looked at the OWASP top 10, focusing on input parsing, authorization, and configuration documentation, which are the main themes that go through these top 10 that are being renewed every couple of years to highlight the main issues out there. That's all that I wanted to tell you about this web application case study. Next week we're going to talk about mobile systems. Thank you very much for your attention, and I'll see you around.